If you have some quantity Q that has a half-life in time, okay, this means that Q gets cut in half, and that gets cut in half, and that gets cut in half, and that gets cut in half, and this gets cut in half, and this gets cut in half, and now I can't really, because of the width of the chalk line, do any more than that. Okay, so it gets cut in half once, twice, 3 times, 4 times, 5 times, 6 times, right?
Mm-hmm.
So I'm going to
You have to get that
subdivide
in.
this. Maybe not perfectly, because it's a little hard to divide something into 3. You know that you can't trisect an angle or line segment using compass and straight edge, right?
Mm-hmm.
You know that? You ever do compass and straight edge constructions in geometry? Terrible, terrible mistake in the curriculum, okay? And it's really we really don't have time to do much with that, but we might do a little. Okay, so anyhow, so we have this quantity, and each of these is a half-life. So these are supposed to all be equally spaced. I didn't quite manage that very well, but there it is, okay? So the quantity is originally this. It cuts to half in a half-life. So these are half-lives. So we have a point here. And then this gets cut in half, so we have a point here. And then it gets cut in half again, so we have a point here. And it gets cut in half again, so now we have a point here, and then a point here, and a point here. And it's clear that we never reach 0 here, because you've always got something to take half of. So this sequence of points here is asymptotic to 0. And the graph is asymptotic to the t-axis, for reasons that should be pretty obvious. So now if we sketch a curve, the curve's going to look like this. Okay? And this is a decreasing exponential function. And this could represent any decreasing exponential function, because I haven't said what Q means or what the half-life is, right? At least any decreasing exponential function of time. And if you have an exponential function of something else, just change the t to whatever that is, right? So that's how you can construct a graph of a decreasing exponential function. And that's all there is to it, if you want to sketch a reasonably accurate graph. Now, this exponential function has some properties, like there's a tangent line. Know what a tangent line is?
Mm-hmm.
It's a line that just touches the curve at one point. Tangent line here, 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 tangent line here. Okay? These tangent lines have slopes. Okay? And of course, the function itself, of course, there's a tangent line up here too. We don't want to leave this one off or it'll pout. Okay? So we have values of the function. The values of the function at these points are, I'm going to indicate by these arrows. Each arrow is half as great as the one before. Okay? Now, property of exponential functions is, this is exponential. These arrows are, each arrow is half as great as the one before, and they're equally spaced along the t-axis, right? Well, the same is true of the slopes. Each slope is half the slope of the one before. Okay? each value indicated by an arrow is half of the preceding value. And each slope is half of the preceding slope. Okay? Now, you haven't proven that this is so, and you probably, most of you aren't in a position where you can totally understand how we can prove this, because it involves binomial coefficients and stuff in a way that maybe we get to and maybe we don't. Okay?
Okay, what did it say? Each value of arrow is half of what? Preceding?
The preceding, each slope, each value is half the preceding, meaning half the preceding value. That's implicit, that's standard English, okay? If anybody still understands standard English, the way people are abusing it these days, but they always do, because language changes. Okay, well, and what's the rate of change of language? How do you measure that?
Let's do that.
You know, one reason we use things like a circuit and measure voltages and stuff like that is because you can do it quickly. We could easily go out and measure the decrease in fish populations in some lake in Canada. We'd have to spend, 5 or 6 years doing it.
Let's
Okay?
go.
Huh?
I said, let's go.
Oh, I love Canada. Incidentally, there was a place in Canada where I did a lot of canoe tripping when I was younger. Algonquin Provincial Park. And I just saw a little blurb. They discovered a carnivorous plant in a bog in Algonquin Provincial Park. It actually eats vertebrates. I mean, I'm just talking little tiny salamanders. But that was kind of an astounding discovery. And I kind of have a connection to that. Anyhow, that's way off the topic here. So we digress, but we come back. Now, okay. So this and this can be proven from basic principles, from stuff that isn't too far from what you should understand. It's just basic, very basic first semester, early first semester calculus. Okay? Just a simple limit. But that involves a little bit of stuff. So, okay. So anyhow, there are a number of properties that exponential functions have. Okay? But that's a good place to start. Now, this relates to what we just observed in our observations. It was a simple RC circuit. Consisted of a high capacity capacitor and a length of nichrome, just plain old common nichrome. It's a heating wire. It's what you use for coils for heater, electric heater. Okay? But Q is voltage. Now we're not going to study the physics of that. And we don't have time to go study the populations in these lakes. Too bad. Canada's a pretty neat place.
We just need to get a good fisherman.
Canadian wilds, huh?
So we just gotta get a good fisherman. We just count him as he catches them.
Yeah, but it's so good that he doesn't mess with the population as he's observing it.
Right?
You throw them back.
That can be tricky. Okay, so anyhow, Q's the voltage. It's a simple
can't
RC
count.
circuit, and
same fish twice.
T is counts of a 2.5 meter pendulum. Now, you've already got a really good model for pendulums. We did that on our first day, right? And you know how we did that. And you did homework on it, and I'll bet you did real well. Okay? Haven't looked at it yet, so I might be surprised, but we'll see. I don't think I'll have too many surprises.
What was the, it was, F equals AL to the T, or to the?
P.
Yeah, frequency is some multiple of the negative 1/2 power of the length. And you figured out what that multiple was if the length is measured in millimeters, and it was about 2,000. Okay? So, yeah, we did that yesterday, and I'm going to kind of let that settle into your brain over the weekend, okay? Because it relates to this, okay? So, for this circuit, this is 4 volts. And this is each of these is 19, which means that your coordinates are what? 19, 38, 57, 76, etc., right?
Where did we get 19?
Because that's how many
Remember
seconds
counting?
it took
Oh,
to
yeah.
get from
Yeah.
4 to.
Okay.
Now, you might have gotten 20, so you might not be thinking 19, because he kept saying it was 20. And you might be right. Fortunately, we don't have video documentation of the counting process, okay? Yeah, we could have done that. I could have turned this camera around, embarrassed everybody. But, no. Okay? So, do we understand what we just saw? Okay? Now, we can write this as a formula. Yeah, we have a formula for the function, very easy to write down, okay? But we're not going to go there right now because we're not worried about the symbols. We want to get the concept. This is a concept of an exponential function, okay? This is a decreasing exponential. Now we're going to talk about compound interest a little bit. And incidentally, the orange juice thing is also a decreasing exponential. Okay? We're going to talk about compound interest since we're on the topic, okay? And it's constructed in a very similar manner. Any compound interest function, especially a continuous one, is constructed in a very similar manner, but we got to start low if we're going to construct this, okay? Because what happens is, this is no longer half-life, this is doubling time. Now, I don't want to even,
This is compound? What would this be called?
Compound interest.
doubling time, which will, actually dt, I'm gonna change that. Because dt looks like a differential. That'll be a standard notation in calculus, so we don't want to confuse, because we will actually, in discrete approximations, be using that symbol. Okay? So I'm going to use t, so d, for doubling time. That doesn't stand for touchdown, because that d is a subscript. It's not touch sub down, it's touch down. So that's time of doubling, right? So what do you think's going to happen? What do you think, what's going to happen to this value of q?
It's going to go that.
It's gonna double.
It's going to double,
It's going
because
to
we have doubling time, right? So this doubles, so it comes up to here. I actually want to start a little lower. So here's our quantity. This point is on the graph. After a doubling time, this quantity will have doubled. After another doubling time, it will have doubled again. And after another doubling time, it'll be all the way up here. And your graph looks like this. Kind of looks like a parabola, but it isn't. Okay? That make sense?
What would you call that curve?
It's an exponential function, just like that one. Okay? This is an increasing exponential function. Okay? Now, if you turn this graph around, flip it this way, did everybody see the way I flipped it? No, because you're making notes. That's okay. I'm glad you're taking notes. Okay? But watch what I do here. You flip it this way, it becomes an increasing.
So a decreasing could be an increasing if it's flipped.
Yeah, a decreasing and an increasing exponential function are really just the same thing if you just flip them. Flip a decreasing, you get an increasing. Flip an increasing, you get a decreasing. And also, now this function here, there's nothing sacred about where this point is. You can keep, maybe the whole thing started over here, but you just started your clock here, right? Like, maybe this is an exponentially increasing population, which is what you tend to get if you put a reproducing organism in an environment with unlimited resources and space. Okay? So maybe this thing's been there for a while, you just started observing it here. And you observe this exponential increase. Well, that means if the process was continuing here, this thing actually does this. And clearly, this isn't a quadratic function. This is not a parabola. It doesn't have a vertex. It just has an asymptote. Okay? It's a totally distinct type of function. Okay? So we have this increasing exponential function. We have a decreasing exponential function. Now we could make analogous statements. Each value here is double the previous value, and each slope is double the previous slope, right?
Wait a minute.
Okay? So that would be an increasing exponential function. Right? So if you understand that much, it's a good start. I could write down formulas. I could write down functions you plug into your calculator. And you'd see that they have these properties, but you don't know how to connect that function to this basic principle. Okay? And the fundamental characteristic of any exponential function the rate of change is in constant proportion to the quantity. And we could write that in mathematical language is delta Q over delta T is approximately equal to K times Q, where K is constant. Now, you're probably not used to reading statements of that nature, so I probably have to talk a little bit more about exactly what that means. I'll say just a little bit right now because it needs to be developed. Delta Q is the change in the quantity, right?
What'd you say? WQ?
Delta Q.
Delta.
Okay. Now, how many of you are familiar with delta as meaning the change in a quantity? Okay, some of you aren't. Okay, that's the Greek letter, capital delta, just a triangle. Okay? And it means a change in Q divided by a change in T. Now, where in your homework did you say something about a change in something divided by another change in something? I heard you talking about it earlier.
Change your
Rate
rate
of change.
and then
The rate of change. Okay? So kind of building up to one of your questions here. Okay, what's this rate of change versus midpoint? Okay? That makes sense?
what's
Yeah,
the,
we want to clarify that.
I have a question.
Okay.
What's the line underneath, above the K constant? Down,
This,
down. That.
it just separates this from this.
So that goes underneath.
This is just a continuation of this. I'm stating that this K is a constant number, and I didn't leave myself enough room to write that as coherently as I'd like,
Okay.
because I didn't know what I was going to write. I was waiting to see what I thought you understood. Okay? That's my excuse, and the other point is I'm not real good at organizing a board. Okay. Make sense? Everything except the point that there's something I'm not real good at. That doesn't make any sense at all. Okay, well, so delta Q is the change in whatever this thing is. Delta T is the change in your time, okay? And this is the rate of change, the average rate of change of Q with respect to T, okay? And we'll talk more about that. And that is approximately equal to some multiple of Q where the thing you multiply by Q is always the same. That's what this statement means. And I say approximately equal, and I don't have room to write any more qualifiers. The implicit idea here is that delta T is a small unit of time, a small change in the time, meaning that delta Q is also going to be small, because if T is small, that's going to make delta Q small, right? So for very small increment of time, very small delta T, like for this thing between T equals 20.7 counts and 20.8 counts. Not that you could actually count that, okay? That would be a small unit of time. You'd have a small unit in the voltage, right? Small change in the voltage, and you divide those out, you get a ratio, and that's going to be proportional to whatever the voltage is. Okay? Again, an idea that needs to be developed. It's not something you immediately understand, but I want to give you the definition. Okay? So this is the starting point of understanding exponential functions. Now, there are other possible starting points. Of course, none of them are as good as this one, but yeah, that's okay. We can tolerate it. Okay? Okay, so let's talk about compound interest just a little bit.